In this session, we'll discuss about fatigue of metals. It has been recognized since 1830s, a metal which is subjected to a repeated stress or the fluctuating stresses will fail in the earliest stages well before when the metal which is subjected to a static load. I mean to say that the metal will be failed in the earliest stages or at the earliest stresses when it is subjected to a fluctuating stress, when it is compared with a metal which is subjected to static loading, right? So, a failure of the metals when it is subjected to fluctuating stresses are called as fatigue failures. So, fatigue failures is insidious because the failure will happen without any obvious warning. And these fatigue failures are brittle appearance fracture. I mean to say that the fracture will happen normal to the principal tensile stresses. And this fatigue fractured metal can be easily recognized by viewing the surface of the fractured surface. There will be quite two different sections, like the soft region will be there or the smooth region will be there, and then a rough surface will be there. This is because initially when the crack is initiated, because of this fluctuating, there will be rubbing action of this crack which is propagating, where the surface will be the smooth, and once the cross section is very less to bear the load, it will fail as a ductile fracture, and also it will suddenly fail, and that surface will be very rough. So the metal which fails due to fatigue can be easily recognized by viewing the surface that will having the two sections. One will be the smooth and the next one will be the rough surface. So at this point, if I define the general types of fluctuating stresses, it will be very easy to design the component which is undergoing a dynamic loading. So various general types of stress cycles are, so let me draw here. Say in this y-axis I'll choose the stress, and x-axis I choose cycles, and the stress may be fluctuating. Here it is completely reversed. Initially it is tension and later it is compression. So this is the maximum stress which is acting, and this is the minimum stress. And this cycle is called as reversed stress cycle. Here the stress is completely reversing. So it is named a reversed stress cycle. And this stress cycles will be mainly made of two components. One is alternating stress sigma A, and another one is an average stress or mean stress, which is indicated by sigma suffix m. So the stress cycle will be having two components. One is this alternating stress and another one is the mean stress, right? So there is another most general type of cycle which will be acting on the machine component is, so here the stress may be repeated but it is not reversed. Say the same in y-axis, it is the stress, it is positive and this is negative, and the stress will be fluctuating in a tensile part itself. So here also the stress is fluctuating, but it is not reversing from positive to negative. And here it is fluctuating in the tensile zone or in the tensile limit or in the positive axis, but the stress is fluctuating. So this is sigma max, and this is the minimum stress. And as you know that this stress cycles will be made of two major components. One is the alternating stress, another one is the mean stress. So here at this stage, if I'll be explaining you how to calculate this sigma A and sigma M from the stress curve. So sigma A is given by sigma max minus sigma minimum divided by 2. So coming into this figure, or here if you notice, from here to here it is the sigma max. If I subtract a sigma minimum, it will be reduced to this much content, and if I divide that by 2, I'll get this zone. That is called an alternating stress, which is sigma A, which is equal to sigma max minus sigma minimum by 2. So sigma M can be calculated by, it is the average or the mean stress, which is sigma max plus sigma minimum divided by 2. So coming to this figure, reverse stress cycle, so this is the sigma max, and sigma minimum is exactly the sigma max. The magnitude will be exactly the sigma max value, but it is of negative. So this equation will be changed as minus sigma max divided by 2, which is equal to 0. So I mean to say that in this condition, sigma mean is 0, and here the sigma mean should be calculated with the equation sigma max plus sigma minimum divided by 2, right? So these are the two stress cycles which we often seen in a machine component when it is subjected to dynamic loading, right? So as I said earlier, a metal which is subjected to a dynamic loading or fluctuating loading will fail much in the lower stress when it is compared with the metal which is subjected to static loading. So how to design a machine component which is subjected to a fluctuating loading? So in order to know that when the material will fail when it is subjected to repeated stress or reverse stress, and usually the people will conduct an experiment based on the reverse stress cycle, and they will calculate the failure. I mean to say that at which cycle the material has failed. So that test is usually a rotating beam test. Usually it is a beam. The weight will be loaded here and it will be subjected to bending and it will be tried to rotate. So in such a case, what will happen? Say initially after adding the weight, if it is of in this fashion, the beam is of in this fashion, then when it is rotating at the next part of the cycle, it will turn to in this fashion. So it means that, I mean to say that the lower part or in the upper part initially is of compression, and the next cycle the upper part will be in tension and the lower part will be in compression. That's how this is reversed in a rotating bending test, and we'll try to plot that result and we'll try to find out how to design a machine component which is subjected to a fluctuating loading, right? Usually a machine component which is subjected to fluctuating loading will be decided by this rotating beam test with the fatigue test data. That will be in y-axis it will be stress, and in x-axis it will be number of cycles to failure. So this curve usually they will call it as SN curve, the stress and number of cycles to failure curve, right? So as you notice that a material which you know that
this video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.
When there is no cycle, just a static load is acting on it, it will fail at its ultimate strength. And when the number of cycles are increased, usually this will be in a log scale here, but here I am writing 10 power 1 cycles, 10 power 2, 10 power 3, 10 power 4, 10 power 5, 10 power 6 cycles, 10 power 7, 10 power 8, 10 power 9 and so on. So as you know that when you just have put a tensile strength, when it is loaded, when the stress is equal to the ultimate strength, obviously that metal will fracture, right? So when I choose the 90% of its ultimate strength, 0.9 of ultimate as the initial stress value or the stress level, by this, and when I increase the number of cycles by rotating a beam, we notice that up to 10 power 3 cycles, 1000 cycles, there will not be much difference in the failure. So it happens exactly at the same stress levels until it is in 10 power 3 cycles. It is a lower cycle, lower fatigue test. After 10 power 3 to 10 power 6, it is noticed that the failure with respect to the number of cycles has a linear fashion. After 10 power 6 cycles, it is noticed there is no much decrement in the stress level for the failure. So if I try to draw a line over that, it is just a constant line and it is varying here, and afterwards there is no change in the stress level. So this will be a usual SN curve for certain metals. And here if you notice, this point is called as the fatigue limit or endurance limit. Here if you notice from the stress to the number of cycles to failure curve, on a metal if you maintain the stress limit of this endurance strength, then the material can withstand for n number of cycles without failure. I mean to say that the metal will have infinite number of cycles without failure if you maintain the stress level of its endurance limit or a fatigue limit. Right. So the test will be conducted for various metals and we'll have various stress to number of cycles to failure curve, and we will be trying to find out the endurance limit of the material. And one more thing has to be noticed, that the metal which we are undergoing with the experiment will be having smooth surface, or where the temperature will be the room temperature. There will not be any corrosion, or the metal will be homogeneous most probably in the test condition. But in reality that will not be the case. It may be an high temperature, or the metal will be corroded somewhere, or the surface will not be smooth. So those factors has to be considered when you are choosing the endurance limit for designing some component which is subjected to fatigue condition. So, and one more thing has to be noticed, for aluminum there will not be a pattern in this fashion, so it will not have a well defined endurance limit of the material for an aluminum, I am saying. But so we usually choose the stress limit at 5 into 10 power 8 cycles as the endurance strength, and near to that 10 power 8 cycles to design a component made of aluminum. Right. So this is the stress to number of cycles to failure curve, and with the help of this test data we'll try to find the endurance strength, and by considering all the factors which affects the endurance limit like surface finish, the temperature, all those factors, after considering, then that value has to be chosen to design a machine component when it is subjected to fatigue loading condition. So as we discuss now, this stress to number of cycles curve, this SN curve, is mainly for the metal which is subjected to reversed stress cycles or some constant value of mean stress which is acting on the beam. So the metal which undergoes this rotating beam test will be in the fashion, usually the stress cycles will be repeated where there will not be mean stress or any average stresses. So this SN curve is for reverse stress cycles. Now the question is, how you will design, or what is the design condition or design strength, design parameter to design a component when it is subjected to the reversed stress, or when it is subjected to repeated stresses or the fluctuating stresses, and it is superimposed by a mean stress. So it is of in this fashion. there will be a fluctuating stress and it is imposed by a mean stress. Where you know this is the sigma max, this is the sigma minimum, and this is the alternating stress. So for this condition, when the metal is subjected to this condition, let's see how to design a machine component. So as you know that when a metal, when it is subjected to only a static load, where the load is not fluctuating with respect to time, or the load is not changing its magnitude with respect to time, in that case you will obviously choose the ultimate strength or the yield strength as the failure criteria when only the static load is active. So that time if you choose any factor of safety, then the design consideration will be sigma u ultimate divided by n, or sigma y by n. So in this case, if the material is having any stress riser, or if there is any change in the geometry in the component, or then there is any notch in the component, then we will choose usually the stress concentration factor. But usually when I design a material for a fatigue condition, I'll choose only the ductile material. For ductile material, I will not choose a stress concentration factor, it is equal to 1. Because, say for example, a metal with this geometry, you all know that this is going to be the stress riser, or the stress is concentrated there. When the stress is concentrated here, the maximum stress is acting, you all know that once it crosses the yield strength, this portion will get deformed plastically, and once the ductile material goes to the plastic stage initially, then it enters the strain hardening zone. So where it takes more load for further deformation. You know that this ductile material, which once it reaches the strain hardening zone, it takes more load for further deformation. So for the ductile material, which is having the stress riser in the material or stress concentrated zone, then no need to substitute the stress concentration in the equation. So I can remove it. Since for a fatigue condition, I always use a ductile material for it. Right. So now, as you know that when only the static load is acting, and this is my condition, the limit for a failure. So same thing, when fluctuating stress is acting, that's what we saw now, the limit is the endurance. And if any factor of safety is consider it, and it is denoted by n, and the value of stress concentration, if any stress riser zone is there, then I have to consider stress concentration of fatigue, or a fatigue stress concentration has to be considered when the load is fluctuating. Whereas in the static, there is no need of considering a stress concentration, because this is the ductile material, where when it goes to plastic zone, obviously it takes more load for further deformation, so I have no need to consider KT or a stress concentration value for the ductile material under static load. So this is the failure limit for a metal which is subjected to fluctuating load. So now the situation is, there is a fluctuating load and it is superimposed by a mean stress. So in this situation, from the test data, so on y-axis I choose the alternating stress, on x I'll choose a mean stress. As you know, the failure criteria is sigma E by kf into n, and only mean stress is acting, I choose yield as a failure. And as we notice that the failure of a metal when it is subjected to fatigue loading condition, or fluctuating load, the fracture surface will be like mostly a brittle appearance failure. So it will be okay. As we are discussing now, a condition that where the load is fluctuating on a machine component and the mean stress is superimposed on that. So in such a case, the design consideration will be, just I am plotting the test result now, where in the y-axis I take alternating stress, in x-axis I choose the mean stress, and for failure limit here is its endurance strength divided by the, I am considering a factor of safety and fatigue stress concentration factor. So now here, when the mean stress is acting only, I mean to say that when there is only the mean stress.
This video is brought to you by Monster Shakes, co-sponsored by TechnoSpark.
Or the static stress is acting on a machine component, I will choose, because it is a ductile material, then the failure limit will be the yield point. So after that it goes to the plastic deformation, right? But as we discussed earlier, that the fracture will be like a brittle appearing fracture where the failure occurs to the normal to the principal tensile stresses. So I choose the ultimate tensile strength by a factor of safety here. So both the things I consider. So from the test result, I plot the test results data. As you know that when there is no mean stress, the failure is going to happen most probably with sigma E by kf into n as your design consideration. As the mean stress is superimposed, then the stress cycle this is going to be my stress data. From this test data, a Gerber has proposed, a Gerber is a scientist who proposed that this can be drawn as a parabola, and he proposed that the combination of stress which falls inside this curve will have infinite number of cycles without failure. Whichever it falls outside will have a finite number of cycles. After finite number of cycles, the metal is going to subject it to a failure or a fracture. So from the Gerber data or from the Gerber proposed method, there is some test results which is scattered. So it is not giving the accurate result, where when we are using some this method which is proposed by Gerber, some of the metals may failure, most metals will be safe, will have infinite number of cycles, but still there are some metals which may fail. So there is a man who proposed a method that can be a straight line between the endurance and the yield, and this is proposed by a Soderbergh. This is proposed by Gerber. It is also called as a Gerber parabola. This is a Soderbergh line. So from this, he proposed whichever the stress combination which falls inside will have an infinite number of cycles, and whichever the stress combination which falls outside will have only the finite number of cycles. So again, from this it is very clear, and these zones are also will have an infinite number of cycles, where the Soderbergh says this are having only the finite number of cycles. So another gentleman who came with an idea that he has drawn a line between the endurance and the ultimate, and this line is proposed by a Goodman and also called as a Goodman line. So now it is so clear that from the test data, Gerber has proposed as a parabolic curve, and since there is some scattered result, the Soderbergh has proposed a line between endurance and yield, and still these are the zones which are safer, which is having an infinite cycles, but he proposed those are having finite cycles. Then a good man came with an idea that can be drawn between sigma E and sigma U. So these zones, he says that all are having the infinite number of cycles. So now I'll ask you the question that if when the metal or the machine component, when it is subjected only with the mean stress or the static stress, so obviously you know that it is a ductile material, then the failure will happen at the yield, then the metal starts yielding at this zone. So it is very clear that when there is only the static stress, the material will fail at this zone. So as proposed by Goodman, this zone is also a failure in the sense it will have a finite number of cycles, but he said that it will have an infinite number of cycles. Then Goodman itself has proposed a line which is a modified Goodman line, which is run between. So now to explain this modified Goodman line, so I'll make here, say this is sigma, this point is its yield strength of the material divided by Kf into the factor of safety, and that line drawn between these two lines, that this line is an yield criterion line or an yield line. So when we are designing a component based on modified Goodman line, we have to simultaneously solve the equations proposed by a Goodman and also this yield line. Whichever gives the lesser value, we have to focus on that. So I repeat, the Gerber has proposed a parabolic curve based on the test result. Whichever falls inside this will have a infinite number of cycles, and Soderbergh has proposed a line between the endurance and the yield. Whichever falls inside will have the infinite number of cycles, and Goodman has drawn a line between yield and the ultimate, and whichever the line falls inside will be having infinite number of cycles. So from our basic understanding, then if the material is a ductile, which I am going to choose for fatigue loading conditions or fluctuating loading condition, only when mean stress is acting, the failure will be the yield. So these regions are unsafe. I mean to say that these zones also will have only the finite number of cycles to failure. So he himself proposed a modified Goodman line. So he has drawn a yield line between y-axis to x-axis, and so now the question arises that how to solve a modified Goodman line. Solve the yield line, write the equation for the yield line, and solve it, simultaneously solve the line for a Goodman, and compare the result, choose the best one or choose the better one. So now with this information, I'll try to put this in a mathematical form. So the mathematical form of this equation is so simple. Before that, I'll just write an equation here. It's x by a plus y by b is equal to 1. Say here, say this is y-axis and this is x-axis, and this is the intercept, and y-axis is b and intercept on x-axis is a. Now this is the intercept form of line equation. I'll try to explain this. So on x-axis, y is 0. If I substitute y is 0 in the equation, then it gives x equal to a. So I'll get the intercept value of x in the intercept value on x-axis. If I substitute on y-axis x is equal to 0, then I'll get y is equal to b. B is nothing but a point which is having the intercept on y-axis. So this x by a plus y by b is equal to 1 is nothing but the intercept form of line equation. With this information, I'll try to write the math form of these lines. So I'll choose first the Soderbergh line. So from the Soderbergh line, this is the Soderbergh line. So the x is sigma m, x is is the mean stress, and the A is for Soderberg, it is sigma y by n, plus y is alternating stress divided by B for Soderberg is sigma E divided by Kf into factor of safety, which is equal to 1. So this is the intercept of the Soderberg line equation. This is the intercept form of line equation, and this is the intercept form of Soderberg line equation. Now we can calculate sigma m by the load which is acting on the Besson component. So we are able to calculate the maximum stress and the minimum stress very easily. So by knowing maximum stress plus minimum stress divided by 2 will give sigma m, and sigma max minus sigma minimum by 2 will give the alternating stress, and the endurance is the limit for the metal, and this is the yield strength which is known for the metal, and Kf has to be chosen properly based on the test results. And by knowing all this equation, I can find the value of n for the given condition. If the value of n is more than 1, then it falls inside this zone, so it means the metal is safe. If the value of n is lesser than 1, then it falls outside. The material will have only a finite number of cycles that has to be calculated, how many cycles it can withstand without failure. Right. Similarly, we can do for Goodman. So Goodman line, when it is compared with Soderberg line, we are changing only the yield to ultimate, so it can be rewritten as, so this is Soderberg line, and for Goodman it is sigma m divided by sigma y by n plus sigma a divided by sigma e, this is sigma ultimate for Goodman, Kf into n, which is equal to 1, and this is the equation for Goodman line. So as we said that earlier, this zone is also will have a finite number of cycles, or it will be a failure, it will be a failure case when metal is subject to only a static loading. It goes to yielding after this. So the yield line will be, this is the yield line. I try to write the equation. It is sigma a, or x by a is sigma m, x is sigma m, a is sigma y by n plus sigma a divided by sigma y divided by Kf into n, which is equal to 1. So this is the yield line. For a modified Goodman equation, solve both the equations simultaneously and choose which one is better. I mean, which factor of safety is giving the lesser value, concentrate on that. So right, the only left is the Gerber parabola, and it is a parabolic, and which takes the power here. Here the power will be 1 in Goodman, and just for a parabolic, the equation will be in the order of 2. So for a parabolic, it will be sigma m by sigma u by n whole power 2 plus sigma a by sigma e divided by Kf into n, which is equal to 1. This is a Gerber parabola. Right. So, as we discussed, that a metal which subjected to a fluctuating load will fail at the lowest stresses when it is compared to the metal, for the same metal which is subjected to a static loading. So now with this analysis, or with this knowledge, we try to find out the design condition, or how to design a component when it is subjected to fluctuating loading. So we end up with most two general cycles which usually are happening in the real time. One is the reverse stress cycle, and another one is repeated stress. The difference is, in the reverse stress, the stress will be completely reversed from maximum to minimum, from positive to negative. In a repeated stress, it will not be reversed, but it will be fluctuating, but the mean stress will be superimposed on that. For these two cases, we have seen how to design. For the first case of reverse stress cycle, I have drawn the stress versus number of cycles to failure curve, that is SN curve, which is plotted between the alternating stress and number of cycles to failure. So from we noticed after 10 power 6 cycles, the failure stress is not changing, it is constant almost. So that stress level we choose as the endurance limit or the fatigue limit. And for a machine component, if we maintain the fatigue limit of a stress level, then it can withstand the number of it can go for infinite number of cycles without failure. And as I said that for some few metals, this endurance limit will not be exist. For aluminum, probably that endurance limit will not be there, where you will not notice after certain limit or after 10 power 6 cycles, the stress level will maintain. There it will be drastically decreasing there. But usually for designing an aluminum, they choose limit as the stress level in the order 10 power 8 cycles. So then after, by knowing the SN curve, from that we choose the endurance limit, and after considering the real-time affecting factors like surface finish, temperature, corrosion, all those factors are considered. After considering that endurance limit will still be reduced, and that we have to choose as the failure limit to design a machine component subjected to the reverse stress. Similarly, for a metal component which is machine component which is subjected to a fluctuating load which is superimposed by the mean stress, this few scientists has proposed that lines from the test data which is fall between the endurance to ultimate, and with the test data Gerber has proposed it as a parabolic curve, and some scattered in the result is there. So Soderbergh has proposed from endurance to the yield, and Goodman has proposed from endurance to ultimate. In a Goodman, they notice that if only mean stress is acting, and after this yield strength, the material will go to yielding, it is a failure. So the modified Goodman line is proposed by drawing a line between the yield in y-axis and the yield in x-axis. So both the equation has to be solved simultaneously and choose the better one. And these are the math form of this equation, math form of this line. By knowing the intercept form of line equation, we just made it for various line proposed by the scientists. By choosing these values, by calculating the value of sigma m and alternating stresses and the properties of materials, we can calculate the factor of safety, which is if it is greater than 1, the metal will be having the infinite number of cycles. If it is less than 1, it will have finite number of cycles. Then we have to work on it, and we have to find for how many cycles it can withstand without failure. Right. So here I end up the session. Thank you.
For more updates, stay tuned to KL Radio, the voice of Kalians. This video is brought to you by Monster 6,
co-sponsored by TechnoSpark.